There's a fairly famous curve called the cycloid, and the cycloid is the path that a point on a circle takes as the circle rolls. So what I'm going to do is I'm going to take this circle and that point, and I'm going to shift it down so it's sitting on my ground here. Then I'm going to copy it, and I'm going to paste in another copy of it here and get it so that it's on the ground. I'm going to overlap them a little bit here. The idea is that as the circle moves along, rolls along the ground, this point will start to move up, right? So it's not going to be on the ground anymore. In fact, if I let me do this in green. If I roll this far along the ground, then I can look at that same amount of arc length and say, well, that's where that red point is now. That red point is now here, and the path that the red point has taken has gone up like that. At some point, the circle will be have rolled through half of its circumference, and that red point will now be up at the top, and then it will continue to roll, and at some point it will have become so that that red point is back on the bottom again, and the path will look something like this. It starts going up, it goes across, and it comes back down again. That's one bump of one arch of a cycloid. It would then repeat itself as the circle kept going. I want to find parametric equations for this curve. Okay, I'm going to put my coordinate system in here. I've already got what I would consider the x-axis. So, yes, and then the y-axis I'm going to put right through here, right through there. That's my y-axis. This is my x-axis. I need a parameter, and what I'm going to use the parameter for is the parameter that I'm going to use is the angle that this thing's rotated through. So I'm going to, blue is good. Look at the center of the circle. The center of the circle started here, and it rolls to here, and then it rolls to there, and it rolls to there. Well, as it rolls, if I look at a line that still goes straight down to the ground, and then out to that point that I was interested in, okay, then this angle that I'm turning through is going to be my parameter, and I'll call that angle, let's give it another color here so it stands out a little bit. Let's give it a purple color here. It's theta. All right, so that angle is theta. Now, how do I find parametric equations? What I need to do is I need to find formulas that tell me the x-coordinate of this point and the y-coordinate of that point. All right. Well, I notice a couple of things. One is that if I drop a perpendicular from here over to there, there's a little triangle in there. And that little triangle really helps me out, because I can see that the x-coordinate of this point would be sort of the distance the circle is rolled minus that segment. Well, we got to do some things here. Let's say the circle has radius r. Okay, so this is r. The length of that horizontal segment is r times the sine of the angle. It's the opposite side. So the x-coordinate right here is going to be this length minus that length. Okay, we said that this length was r sine theta. But what is this length? Well, this length is the same as the arc length. The arc length is the angle times the radius, r times theta. So the total distance the center of the wheel has rolled minus this little bit would be where that point still is. Okay. Notice that by the time you've rolled out to here and the angle is pi, well, the sine of pi is going to be 0, and so the distance that this point has moved, the x-coordinate, is the same as what the center has moved, right? It's moved over, and that's the same. So it kind of lags behind the center for a while, and then it catches back up again. Actually, the r theta is exactly where the center is. So you've got the x-coordinate of the center with this function, which starts off, subtracting a sine curve, so you start off behind a little bit, and then when theta gets big enough and the sign becomes negative, the negative will be positive, and all of a sudden this point will be out in front of the center. What's the y-coordinate? Well, the y-coordinate is this height right here, which it seems to me is the radius of that circle minus this little piece. Well, that little piece is in this triangle again. It's the adjacent side to this angle, so that little piece right there looks like an r cosine theta. So I want r minus r cosine theta. I'm going to switch over to the computer here in a moment and take a look and see if this really works. But one thing I want to point out is that these parametric equations come in two parts. One part is this stuff right here. That stuff right there is the motion that describes the motion of the center of the circle. There's also this stuff over here. That stuff over there, actually with the minus signs, right, is describing circular motion, because it got a sine and a cosine working together. So the motion of the point itself is just circular motion around a moving center. This is describing circular motion. This is describing the moving center point. Okay? If this were just a constant, then I'd be describing a circle around a fixed center. But now my center is moving. Okay? So let's switch over to the computer and plug this in and see if it really looks like a cycloid. All right, so here's my online graphing calculator, parametric curves section of it. So I'm going to type in here r times theta. Well, we're going to use t for theta instead. We need to pick a radius here. Let's give this cycloid radius. Let's say the radius of my circle is 2. All right. So I've got 2 times t. Actually, let me just do this first. 2 times t and 2. Right? That is describing just actually, I'm going to move this over so I can see it. That's just where the center of the wheel would be. It's at a height of 2 and it just stays there going across, right? Let me just double check what I'm doing from 0 to 2 pi, okay? So, but what I want to do now is I want to add on to that the circular part of it, the part that's making that thing go around. So I say plus, actually minus, 2 times the sine of t. Oops. And on this side I need to subtract 2 times the cosine of t. Oh, I used an r and it doesn't like r. R is 2 here. There we go. There's one bump of the cycloid. In fact, if I plot more of this, let's plot all the way from negative 2 pi. Whoops, negative pi. How about negative 2 pi? 2 pi. So there's 2 bumps of it. The more I plot, the more you can see that it just keeps repeating itself here. There's 3 cycles of the cycloid, right? That's the path that a point on a circle takes as the circle rolls along a line. Okay. Yeah. The next thing I'd like to do is a similar thing, although let's do it with rolling the circle along another circle. That's the next video.